Alright, hi, welcome back. This is the Bit-Mage. Welcome to SAS X13. I've moved on to recording the SASs at night now rather than during the day. So rather than dawns, I'm doing them just pre-sleep. So yes, that's an update. And rather than having coffee, I'm having tea, caffeine-free tea. So it's not actually tea. There's no tea leaves in it, but it's symbolically a warm beverage. Uh, yeah. So rather than discussing the contents of my tea, let's just discuss about general analysis. That's what I'm going for today. I've been thinking quite a lot about framing a general solution or framing a general problem solver. So one of my SASs quite a while ago was on formulating problems, and a lot of abstractions that I talk about, a lot of techniques and toolings that I sort of chance upon are mostly generically applicable to a lot of things. So general analysis is something that should be a toolbox, a generic toolbox, sort of a diagnostic toolkit that you can throw at a lot of abstractions and get to sort of check the state of the problem and sort of give you a domain specific directive as to where you could further explore your options of for a solution. So uh, the way an analysis could be done, of course, there has to be an incentive for every analysis as to why do you want to even get into the thing, why do you want to understand the thing, what's it going to serve. So those particular objectives are nice to have, but uh, there's a whole bunch of general things that could benefit uh, could benefit to the abstraction being analyzed without influence from the objectives. So these general things, I mean, I've been trying to observe patterns, so the patterns do arise, but then trying to say frame it for an abstraction, for an abstract idea, for a very intangible idea, let's say that could very generically be applicable to any problem. That is sort of an interesting challenge. It's one of the harder things out there in just formulating a general problem solver. So a general problem solver would of course start out with a general analysis, uh, sort of an unsupervised learning kind of thing, an unstructured way to go about things. But rather than data right now, rather than statistics, symbolically analyzing concepts and critical thought that goes into giving you directives as to where you could further explore ideas and solutions relating to the problem. So even before having solutions to the problem, having a language in general, having a language to frame the problem better, a domain specific language is sort of a good way to go about things. So there's sort of different parallel initiatives that I would take to sort of solve a problem in general. So forming a DSL is probably one of the first things that I'd go into, trying to understand when forming the DSL. Of course, choose your axioms. You don't want to start from quarks and electrons and protons and neutrons for every problem out there. You want your own axioms. So choose your axiom sensibly. Now, choosing your axiom to further define whatever you're going to analyze and whatever findings you have is usually implicitly done for you whenever you're getting into things. It's based on the context that you carry. So you probably should try and be more aware of that. So trying to deal with abstract problems then based on axioms that you're aware of is going to be easier than something that is handed off to you, something that you're not truly aware of. So choosing your own axioms, and sort of reasoning about why this is a healthy level of granularity or a healthy level of granularity and abstraction. So choosing that happy medium as to what's your bottom level. What's your basement. That would first of all help out quite a lot. And then the way you sort of build up on it is there's a first generic ways to do it. So once you have your foundation, once you have your basement, and once you have your ground level that's decided, building up the foundation to decide which particular area you should explore in depth, or if you continue the analogy, to build with more heights, to build upon with more heights, with more effort, is to first of all lay generic foundations. So those generic foundations can be laid in different sort of analyses. So this video is about trying to frame that general analysis. So what usually we can do is from the get-go, what comes to mind is framing different axes of analysis, or dimensions of analysis, and given each dimension goes in two directions, a symbolic dimension goes in two directions. Yeah, there's two ways to explore for each dimension. First of all, we could start out independently analyzing the dimensions across the two axes. So for example, if I am dealing with a problem, and let's say, okay, so what do I actually analyze across the dimensions? The best way I can frame it right now is the notion of context, or the notion of state. If you have a programming background, the idea of having a state of an environment, something that in which you evaluate whatever you want to evaluate, the state, the context. That is what I would start out by trying to evaluate over variations of the dimension. So for example, if there's a dimension of time, I would evaluate the context of the problem in the past, the present, and future predictions of it, future anticipations of it. So temporality, that's one orthogonal dimension. Another orthogonal dimension that could be used is, let's say, the scale or the size of the thing, scale or size of the problem, the effect it has. So based on how the context, the state of the problem varies based on scale. Now defining the parameters of the scale as to how you're actually choosing how to understand scale, that is again another exercise. So parameter engineering, so to say, not parametric, parameter engineering would be a nice, or unit engineering own units, or proper indicators to analyze that orthogonal dimension would be sort of interesting. That is another facet to it. So we looked into time, we looked into size. So there's a whole bunch of other things that would come in like this. So for time as well, you could of course, units in here are pretty obvious, but you could also either have continuous variations in time, so you could think in seconds, years, or you could have symbolic variations in time, as in you could think in discrete milestones or discrete events with arbitrary amounts of continuous time between them. So these sort of this idea of discreteness and continuity, this intermix of symbolic variations, timestamps, events, and this continuous gradation over which you can observe variation over smaller granularities, that is sort of interesting. So in size as well, you could have either criterias or the categories, discrete categories, small, medium, large t-shirt sizings, or you could have continuous variations based on a metric that you engineer. So parameter engineering is sort of a nice thing to get into. A lot of people might also interpret it as representation learning. So if you're dealing with abstractions, we'll not probably deal with a lot of dimensions like that, not tensors. So we'll probably deal with a lot of discrete variables, and to understand the units, the proper units under the context for a discrete variable could be a nice start. So there's sort of general thought that goes into it. So right now what we've broken down it into, that could be orthogonal axes of analysis. We just taken two, for instance. One is time and the other is scale. Based on this, we tried breaking it down into different ways we could analyze the context being varied across the state being varied across the combination of these axes. So you could either individually analyze these or analyze these with a combination. So for example, if you wanted a combination, probably over time the scale of a particular state or context will vary. So that variation as a function of these two axes could also be analyzed. So right now we're just discussing two. There could be a whole bunch, and this sort of general analysis, rather than being attached specifically to a particular problem in terms of, say, let's say size or time or anything else that I want, it could be generalized. So let's say rather than having two dimensions, I have n orthogonal axes, and each of these orthogonal axes could have different parameters upon which the context or the state is being evaluated. So your context or your state could be modeled as a function of a tuple being the combination of the different metrics that make up these axes. This is a symbolic way to denote context as a function of your input parameters. Now this, of course, this state space, the state space in this particular context is probably going to be very complicated and cannot be modeled. It will not one will not be able to model it as you might be able to in usual problems that humans encounter, mathematical problems. It's more of a mixture of a discrete and a continuous space. So a tuple is basically, so trying to imagine it in two-dimensional, three-dimensional and n-dimensional spaces geometrically is probably not fair to the problem in itself. So abstract spaces is probably a nice way to go about it, and to evaluate the state as a function of these inputs is sort of a nice way to go about it, is what I feel. Now, how do you actually think of state? A very immediate way is to think of it as a very obvious way for an engineer might be to think of it as a scalar field or a vector field. So given whatever you choose, if your state is a vector field or if it is a scalar field, probably the output space should be free, as in it shouldn't be bound by such restrictions if you're going to do general analysis. So again, the output would probably also be better engineered as a tuple rather than being attached to a specific number or a collection of numbers. It's better engineered as a tuple, which is a mixture of symbolic and tensoric or vectoric outputs. So a function going from an abstract space to an abstract space, I could start defining an abstract space as a combination of a tensor, different tensors and different symbols. Symbols could be categorical variables or just a different kind of space in itself. So I could try framing. I could try giving it a name rather than an abstract space. I could just say a semiotensoric space. A semiotensoric space being a combination of symbols and tensors altogether, and a function mapping that to another semiotensoric space. So transformations between semiotensoric spaces could summarize the whole idea of doing an analysis. So a semiotensoric space should be able to semantically and mathematically convey how the current context or state varies based on how you change parameters. And given that we're sort of plotting this abstractly in an abstract semi-tensoric space, we could sort of include a whole bunch of calculus within it. We could sort of probably include a whole bunch of different ways. We could analyze rates of change based on a certain dimension. So partial derivatives, the idea of partial derivatives comes in. So given a particular size, how the state varies based on time, or given a particular state in time, let's say the future, we fix a line in the future, how the state would vary based on changes in the size. So those sort of partial derivatives sort of come in. We could analyze the gradients of the state function. Now, given that the state function is not a scalar outside per se, we'll probably have to analyze specific parts of the state function to optimize for them. Rather than saying the state function, I should just say the state semiotensor, probably the semiotensor, the state semiotensor. Gradients, the nabla for such an abstract notion would probably not be feasible. So let's say if we wanted to partially optimize something of the state, we could have derivatives for that, partial derivatives for that. Now, we of course cannot partially analyze rates of change on semiotic dimensions. So we'll have to do on the tensoric dimensions. And on the semiotic dimensions, we could probably have abstract rates of change, abstractions. So high or low, we'll probably have to learn a way to express that. So what this is getting into is a way of framing general analysis. So there's this framework of, let's say you've given it a function to predict the state, to output the state at a given combination of semiotic and tensoric inputs across different orthogonal axes. You would be able to sort of actually do a whole bunch of math on it, abstract and tangible. Okay, I don't know if any math is tangible, but yeah, abstract math is more abstract than what the usual math we think of is. And yeah, I think that's enough for today. So yeah, that's enough for today. Thanks for tuning in. This was all about general analysis. This was supposed to be an index into how one could sort of start framing a general analysis framework. So rather than having to rely upon starting from scratch all the time, you could just throw this generically at a domain, and it would start building its own DSL from the get-go and start analyzing things in this semiotensoric space, and go ahead with producing reports for you. So this generic analyzer could sort of come in handy. These are just the sort of I don't know, top of my head thoughts, but let's see where this goes. Thanks for tuning in. This was the Bit-Mage. If you do like this sort of these sort of rambles, these sort of idea potentials, I mean, this idea has potential, but then yeah, I'm just exploring, I'm just thinking in the wild. Do subscribe, and if you are into what I'm talking about technically, if you are sort of aware of what I'm talking about technically, do check out the Bit-Mage. That's where I explore the math, the programs, the computer science of it all, and that's where I get into the how of it. This is actually the what and the why, but that's the how of it. Thanks for tuning in. This was SAS X13, Serendipity as a Service, General Analysis. See you in the next one.